Hello everyone, and welcome to another session of Computational Algebraic Geometry. Today we will be talking about monomial ideals. Our division algorithm used a lot of monomial cancellations. So what we want to do now is to take this a little bit more seriously and focus on precisely this aspect. Now, cancellation of monomials in a certain polynomial really is all about taking a quotient again. So we want to take the quotient of our polynomial ring by an ideal that's generated by monomials. And so this is what we need to study today. Let's make this official and let's define monomial ideals properly. So an ideal of a polynomial ring will be called a monomial ideal if it is generated by monomials. Of course, you could have a non-monomial basis, but in the end, if I can find a monomial basis for it, then it's a monomial ideal. So there's a convenient notation to denote monomial ideals. We want to write the exponent vectors or a set of exponent vectors and then consider the ideal generated by monomials with those exponent vectors. So for a given possibly infinite set of exponent vectors A, I consider the ideal generated by x to the alphas for alpha and A, and I'll denote this by I subscript capital A. So we make the following very simple observations about monomial ideals, and I leave it to you as an exercise to prove them. First of all, a polynomial is inside a monomial ideal if and only if every term of f is inside this monomial ideal. The next property says that any monomial is inside a monomial ideal if and only if one of your generators divides my monomial. So let's write it like this. So x beta is inside the ideal if and only if there exists an alpha inside this generating set such that x of alpha divides x of beta. So this requires another split second of thought to go in one direction. But nevertheless, it's an easy exercise. And I will rewrite this again in a slightly more visual way. So we will say, again, a monomial is inside of I of A if and only if beta is inside the following set. I take the union for each alpha in A of the translations of these domains. So here the term upstairs, so this expression here, x alpha divides x beta, this just means that x beta is x alpha times x gamma. In other words, beta is alpha plus gamma, which of course is inside alpha plus n. Right, so I've rewritten this expression, but this is perhaps a little bit more visual, and we will put this to good use. And I claim that these three properties completely describe a monomial ideal. First of all, you say that we're not interested in trying to find out which polynomials is inside an ideal, because that's equivalent to figuring out which monomials are inside the ideal. This is statement one. So I can reduce trying to understand an ideal by trying to understand all monomials inside the ideal, and trying to understand all monomials inside an ideal really is understanding this union over here. And this is essentially a combinatorial description. So let's do an example and see these three observations in action. So let's take A, my exponent set, to be the following. Well, before I write it down, I should say that I just put a bunch of points on a plane and then recorded their coordinates. So they don't mean anything interesting, so you can do it yourself as well. Okay, so I'm thinking about polynomial ring with two variables, and these are the exponent vectors. Let me draw the picture from which I've translated these coordinates. Okay, I've plotted my n2 basically. Now I'm plotting the points A inside of here. So this is 2, 5, the first point. Let's do the other ones. 3, 6. Okay, I've plotted my points. And the point of this example is to understand this condition about putting and translated copy of n2 at every one of these points. So remember, let's go up a little bit. I want to understand this union of n2 in this case, translated by every element of A. So let's put these pictures in place. For example, if I were to draw, this would be a copy of n2 placed at this point, and I would draw another copy of n2 drawn at this point. For example, the first quadrant that I shaded became redundant already because it's already shaded by this other point here. And I do it again here, once again here, and now here. So a bunch of these points became redundant. The only important points are these 3 corner points. So if I know these 3 corner points, I can recover this shaded region by just putting the translated quadrants at these 3 corners, and then I recover my ideal, because the condition says that the union gives me the exponent vectors of all monomials inside my ideal, and from this I can recover all polynomials. They're just linear combinations of all these monomials. For example, I can write that my ideal now has this simple basis, x squared y5, that's this one, the other one is x4 y4, and then x5 y1. And another conclusion from this thing, which I think is readily believable whenever you have a 2D picture, it looks like whenever I take an A, even if there are infinitely many of them, I think you can convince yourselves that there should be finitely many corners, so that there would be a finite monomial basis. Just take the exponent vectors corresponding to these corners. This is in fact true even in higher dimensions, and it's called Dixon's lemma, and this is now what we turn to. So in the next section, we will state and prove Dixon's lemma.